In mid-2022, a war game simulation of a Chinese invasion of Taiwan was conducted by the Center for New American Security, CNAS, a bipartisan, non-profit Washington, D.C.-based organization, and was broadcast on an episode of NBC's Meet the Press. The center organized two groups of leading experts, one representing China, represented by several experts on China along with the CEO of CNAS, and one representing the United States Security Council advising the U.S. president, which included defense experts, a retired Air Force general, and several sitting members of Congress. Their simulation ran just short of a week real time and was stunning in several aspects. One of the most sobering was how fast China was willing to use nuclear weapons. The team representing China decided after the US and Allied forces' navies were close to defeating the Chinese Navy's support of the invasion to implement what's known as a HEMP shot, that is a high-altitude EMP attack, an electromagnetic pulse caused by a nuclear weapon, high over the U.S. naval forces. Although the Chinese Communist Party, the CCP, has declared they will not use nukes first, it's clear their position on their nuclear weapon force is changing. According to most sources such as the Center for Strategic and International Studies, or CSIS, China is both modernizing and expanding its nuclear weapons arsenal, with the possibility that their current status of using their nuclear weapons for only defensive deterrence possibly changes in the future. Unlike China, Russia does not have a no-first-use policy and has threatened to use nuclear weapons multiple times since its invasion of Ukraine in 2022. They've repeatedly said that if the territorial integrity of Russia seems threatened, nuclear weapon use might be considered. This isn't just President Vladimir Putin saying this. As recently as January 2023, Vyacheslav Volodin, chairman of Russia's lower house, the State Duma, threatened Europe and the US with global catastrophe if the West's military aid to Ukraine passed some metaphorical line in the sand. Other threats have come from former Russian President Dmitry Medvedev, who's talked about the use of nuclear weapons more than once since the outbreak of the conflict in February 2022. And Putin himself warned the West on September 21, 2022, that he was not bluffing when he said Russia would use all available means to protect Russia and our people. He tried to blame the West for ratcheting up the nuclear rhetoric, saying this is not a bluff, and those who try to blackmail us with nuclear weapons should know that the weather vane can turn and point toward them. As recently as April 25, 2023, the Russian Foreign Ministry's head of nuclear non-proliferation, Vladimir Yermakov, told the Russian state news agency TASS that it was the U.S. that was escalating the risks of nuclear confrontation through its opposition to its war in Ukraine. The most acute threat today is associated with the danger of nuclear escalation as a result of a direct military confrontation between nuclear powers, Yermakov said, meaning the US and its allies, including NATO, versus Russia, and these risks, to the deepest regret, are steadily growing. But how would this nuclear attack be carried out? Most analysts think an all-out nuclear exchange is unlikely, since that's the basis behind the no-win strategy known as MAD, mutually assured destruction. Russia and the US both have enough nuclear weapons to assure complete annihilation of the other many times over. China, while still building up its own nuclear forces, has enough to take out every major city in the US if they decide to join in. However, Russia categorizes any high-altitude EMP weapon as part of its information warfare branch, alongside cyber warfare and other electronic attacks. So, their already loose restrictions against using nuclear weapons may not even apply to HEMP weapons, according to their definitions. Make no mistake, an EMP attack, especially one at a high enough altitude that could encompass large areas of the US, dubbed a HEMP attack, has been considered an existential threat to our future. Yet the US is woefully unprepared for the effects of such an attack. Is Russia preparing for an EMP attack on NATO or the US? Russia is already well underway in preparing for such an EMP attack. Since the early 1960s, the former Soviet Union had conducted tests that demonstrated the destructive potential of the EMP pulse generated by nuclear explosions. Their awareness began with a high-altitude EMP explosion known as Test 184, conducted on October 22, 1962 over modern-day Kazakhstan. Even though the technological state of Kazakhstan in 1962 was relatively primitive by today's standards, it was heavily industrialized and fully electrified. Test 184 was detonated above a point 180 miles west of the city of Zhezkazgan, chosen because of its central location in the middle of Kazakhstan. At an altitude of 290 kilometers, the distance to the horizon would have been more than 1,900 kilometers, and the electromagnetic pulse generated by the explosion would have covered the entire region. This was done deliberately for the Soviet Union to see what effects the EMP would have on a populated area. The EMP effects from Test 184 destroyed transformers, generators, communication systems, electric switches, and all types of electronics within an enormous area extending hundreds of kilometers, thus proving the effectiveness and destructive potential of nuclear weapon-generated electromagnetic pulses. The results of Test 184 were kept secret for over 30 years and were only shared with the West in a briefing by a Russian general in 1994 after the breakup of the Soviet Union. Test 184 confirmed for the Soviets in 1962 what the United States had concluded earlier that same year from its own tests conducted over the Pacific Ocean, called Project Starfish Prime. Starfish Prime witnessed the explosion of a hydrogen bomb detonated 250 miles above the Johnston Atoll in the Pacific Ocean. The 1.4 megaton bomb, 500 times as powerful as the one that fell on Hiroshima, was one of the last high-altitude nuclear tests, though it was dwarfed by the USSR's Tsar Bomba explosion the previous year, which clocked in at 50 megatons. While the Starfish Prime electromagnetic pulse reached Hawaii, 750 nautical miles to the northeast, it caused blackouts, blocked radio transmissions, and caused significant electronic faults both on land and in numerous ships located throughout the area. On top of the problems of the EMP damage, the Starfish Prime test also created a new artificial radiation belt that was stronger and longer lasting than scientists had predicted. This unexpected starfish belt, which lingered for at least 10 years, destroyed Telstar 1, the first satellite to broadcast a live television signal, and Ariel 1, Britain's first satellite. It came as a surprise how bad it was and how long it lasted, and how damaging it was to satellites that flew through the area and died, said David Siebeck, a scientist for NASA's Van Allen Space Probes mission. The resulting dangers exhibited by Starfish Prime and Test 184 convinced the US and the USSR to agree to sign an atmospheric test ban treaty concluded the very next year. Though underground nuclear testing has continued as recently as 2017 by North Korea, no further atmospheric tests have been conducted. This is both reassuring and troubling. Without further testing, it's unclear just how damaging a hemp explosion would be, which means we're unsure how much protection our electrical grid and computerized systems need. The different components of an EMP attack. From the data collected by these two tests, as well as a few prior atmospheric tests, we've learned some significant elements of EMPs. We now know that when a nuclear device goes off, it generates three significant and distinctive waveforms of gamma radiation, usually denoted as E1, E2, and E3. The E1 component is incredibly brief, only a microsecond in duration, and is produced when gamma radiation from the nuclear detonation ionizes or strips atoms from molecules floating in the upper atmosphere. This is known as the Compton effect, and the resulting current is called the Compton current. The electrons travel at relativistic speeds or close to the speed of light in a mostly downward direction, since there are more atoms lower down in Earth's atmosphere than higher up. This radiation travels in a direct line to the horizon, which is why EMP weapons are expected to be detonated at higher altitudes, from 100 miles up and higher, so as to have the effect spread out as far as possible and affect as much area as possible. However, like all energy, the strength dissipates over distance, so the most powerful portion of the pulse will be directly below the explosion. The E1 component produces high voltages in electrical conductors and can destroy any embedded computers and modern equipment like vehicles, airplanes, laptops, cell phones, and modern communications equipment, as its voltage increases too quickly over just a few nanoseconds for ordinary surge protectors to provide effective protection from it. Shielding can prevent this damage, but usually only sophisticated military equipment or specially constructed Faraday cages are strong enough to protect from such an attack. Following the E1 component is the E2 component, a longer frequency pulse that lasts from a microsecond to 1 or 2 seconds long. The E2 component bears a lot of similarities to lightning, though a close lightning strike might be more locally intense than the overall energy of a nuclear weapon-induced E2 component. Because of the similarities to lightning-caused pulses and the widespread use of lightning protection technology, the E2 component is generally considered to be the least harmful and the easiest to protect against. However, it arrives instantaneously following the E1 component, which may have damaged any surge protections, rendering them useless in protecting against the E2 component. What might be the most damaging to the United States would be the third component, the E3 portion of an EMP. This component is very different from the other two major components of a nuclear EMP. The E3 component is a very long wavelength and a very slow arriving pulse, lasting tens of seconds to several minutes, as the nuclear detonation forces its way through the Earth's magnetic field, followed by the return of the magnetic field to its natural place. The E3 component has similarities to a geomagnetic storm caused by a very severe coronal mass ejection, or CME, from our Sun. More on that later. Like a geomagnetic storm, the E3 component produces geomagnetically induced currents in long electrical conductors like power lines, which can then damage or destroy components such as power transformers. Since the E3 waves are much longer than the E1 over 2 waves, they sync up perfectly with the long wires of our electric grid, which act as conductors for the EMP's destructive energy. And here is where an EMP weapon can deal significant, some say catastrophic damage to the US. As the E3 pulse overloads the electrical grid, it can short out transformers over vast areas, leading to regional blackouts encompassing multiple states because of transformer core saturation and imbalances between supply and demand of electricity. These transformers are huge, very expensive, and many are uniquely designed and built for specific locations or purposes. It could take years to replace them, and without regional power, even building new ones to replace the overloaded ones might be impossible. When you combine the effects of the E1 component knocking out computerized systems and transportation, and the E3 component knocking out significant portions of our electric grid, it's not hard to imagine how the entire US economy could be seriously disabled. It's also easy to see, even if the real damages to equipment aren't that significant, the widespread result of an EMP attack plus its potential impacts on other systems like computers and telecommunications, not to mention food and fuel deliveries, has the potential to make the process of getting things back online seem nearly impossible. What would happen to people and structures on the ground during an EMP attack? As far as we can tell from the existing data, a high-altitude EMP explosion would cause absolutely no physical damage to anything or anyone on the ground. When a nuclear weapon is detonated at 100 miles or higher, its effects are too far away to affect the ground with its blast radius. It doesn't interact with the ground, so it doesn't cause nearly as much radioactive fallout as a near-ground burst, which picks up dirt or ocean water and irradiates it, allowing it to spread across vast regions. Though, as we've seen from the Starfish Prime explosion, atmospheric radiation does exist in at least small quantities and can harm existing satellites, especially if they're orbiting low enough to encounter a resulting and often long-lasting radiation plume. As already discussed, the biggest problem by far is the damage done to infrastructure like the electronic grid, transportation, communication, including both cell phones and the internet, and anything that relies on these systems to do everyday business. The resultant problems from losing power and the ability to move vital services like food, water, gas, heating homes, and running hospitals would be as bad as anything we've seen in US history. Imagine no power to keep food cool in the summer, or no electricity for hospitals to conduct surgery, or even no electricity for the pumps in our sewage treatment facilities. Modern society is wholly dependent on electricity. Without it, we'd revert to nearly Stone Age living, burning any available wood to boil water and heat homes. We've seen how quickly society breaks down when something as regional as an ice storm cuts power. In February of 2021, Texas experienced a severe ice storm that cut power to as many as 5 million residents at one point, with a peak loss of power affecting more than 11 million. Power outages coupled with unusually cold sub-freezing temperatures resulted in the deaths of more than 700 people and damages exceeding $195 billion. People that survived power loss extended in some areas for more than 2 weeks said it seemed like the end of the world. In order to heat their homes, people burned furniture, books, clothing, even children's toys. The lack of firewood became even more extreme when the state government urged 7 million residents in Dallas-Fort Worth area and the Houston and Tyler metroplexes to boil water due to contamination in water lines caused by the lack of water pressure from frozen and broken water lines and pumps. This was all caused by relatively limited effect storm, though it did strike many populated areas and at a time when temperatures hit record lows in a state that wasn't well prepared for either the damage to its power grid nor for the vast numbers of people lacking proper heating and food supplies. Scaling up such effects on a national level could mean, according to some preppers, people preparing for an end-of-time Times-like scenario, and according to doomsayers preparing for a world that devolves to Mad Max levels of anarchy and brutality, they foresee extreme problems for urban areas and expect such problems to begin to occur in as little as 10 to 12 hours after all the power goes out over a vast area. Are Russia and China preparing super EMP weapons? It must be noted that the original fusion-type nuclear weapons, the so-called hydrogen bombs, were created in such a way that they actually, although unknowingly, minimized the amount of EMP damage that they produced. In that respect, many analysts consider those earlier weapons to be suppressed EMP weapons. The E1 pulse these weapons generate arises from gamma rays and from the effects of those gamma rays hitting the molecules in the upper to mid-stratosphere in the presence of a strong geomagnetic field. So anything that prohibited or held back those gamma rays lessened their effect on the atmosphere. These early weapons, 1. Used a very thick and dense layer of chemical explosive around the nuclear material to trigger the reaction. 2. Used a very thick and dense steel casing on the entire exterior of the weapon. 3. Set off a very small fission explosion microseconds before the major, mostly fusion, thermonuclear explosion. And 4. Detonated the device where the geomagnetic field is relatively weak. Because of this, the EMP pulse that they generated was many times less powerful than it could have been. The Soviets quickly learned that they could develop a more powerful EMP weapon by removing most or all of the characteristics of the original hydrogen bombs, simply using more modern materials to eliminate the dense chemical explosives around the fusion core and building the bomb with the thinnest casing possible, even if the casing has to be so thin that it sacrifices some of the explosive power of the weapon, would potentially increase the number of gamma rays emitted from the weapon by a factor of 10, resulting in a huge increase in the EMP pulse created. Another mitigating factor was the region where the US conducted the Starfish Prime and other earlier atmospheric tests. Most of them were done in near-equatorial regions of the mid-Pacific, an area where the geomagnetic field is considerably weaker than other areas of the globe, or in the South Atlantic anomaly, where the geomagnetic field is at its very lowest, where 3 of the first 6 high-altitude nuclear tests of the United States were performed. In fact, the US had already stumbled upon the recipe for creating a more powerful super EMP weapon without even knowing it. According to Chuck Hansen's The Swords of Armageddon, the Starfish Prime Python weapon used a nuclear primary called Python. It was surprisingly compact with a diameter of 17 inches and a length of 26 inches. The Python primary was dense, weighing in at 218 pounds, but all by itself it produced a nuclear yield of 15 to 20 kilotons. Since the Python device was optimized to produce X-ray and gamma radiation, it would likely have produced much greater EMP if detonated alone outside of the Starfish Prime warhead casing than the suppressed EMP actually produced by the Starfish Prime weapon. Rather than knocking out only 300 streetlights in Hawaii, the much smaller Python device of 1962 would have likely knocked out many thousands of streetlights. There have been many claims about the existence of more modern super EMP nuclear weapons that can generate electric fields of 100,000 to 200,000 volts per meter. The declassified scientific literature only describes the operation of first or second generation nuclear weapons which are capable of producing a maximum EMP field strength of about 50,000 volts per meter on the ground. And this only applies on the side of the surface closest to the equator. Maximum field strengths near the horizon would be limited to about half of this value, or 25,000 volts per meter. The reason that the maximum field strength is slightly stronger to the equatorial side of the detonation point, in other words south of the detonation in the northern hemisphere, is that this is where the high-energy Compton electrons start to move through the Earth's magnetic field at a nearly 90-degree angle. We can't be certain, but many government officials and nuclear researchers worry that Russia, China, and possibly other adversaries like Iran and even North Korea might have designed and built nuclear weapons like those described above that can generate a burst of 200,000 volts per meter below the detonation and 100,000 volts per meter near the horizon. Neither the Russian nor Chinese governments have admitted to designing, building, or testing any kind of super EMP weapons, though since it's been made public that the US has declassified documents about their own such programs, it's likely that they have at least kept up with the US and possibly even surpassed its capabilities. And with the relatively simple construction process and small size of such a device, it's not impossible to theorize that countries like Iran and North Korea could also create such weapons and even launch them on easily available short-range missiles from platforms like cargo ships sailing off either US coast. Should we worry about EMPs from other sources? As worrisome as nuclear weapon-generated EMPs are, there's a source far more common and much harder to regulate and control that we should be worrying about: our own sun. The sun has an 11-year cycle of low sunspot activity followed by peak sunspot activity. These sunspots are caused by twists and turns of the sun's magnetic field. At the end of each of these cycles, the sun's magnetic field actually flips, where north becomes south and south becomes north. The solar flares connected with sunspots often reach far enough out into space that they can have an effect on the Earth, if the side of the sun with the solar flare is facing toward Earth at the time. During such events, we might see an increase in the aurora borealis as the electrified particles interact with Earth's magnetic field and travel down through our atmosphere at the two poles. But there are much more powerful eruptions called coronal mass ejections, or CMEs, that are not the same as solar flares. While both are created by the sun's magnetic field, a solar flare is minuscule in comparison to a CME. CMEs are closest to the effects of the E3 component of the EMP blast, but on a much greater scale. While you can think of a solar flare as the muzzle flash of a cannon, a CME is a cannonball flung out by that same cannon. Any sufficiently active solar cycle can create a CME, which carries an EMP component powerful enough to do significant damage to our power grid, satellites, even our very atmosphere. While a solar flare is usually confined to the upper atmosphere of the sun, a CME is an immense cloud of magnetized particles hurled far out into space, traveling over 1.6 million kilometers per hour, around 1 million miles per hour. The ejected solar plasma can take up to 3 days to reach our planet, though some extremely powerful CME events reach us much faster. The differences between solar flares and CMEs are quite different when seen through solar telescopes. Solar flares appear as bright but localized river of light, while CMEs appear as a massive fan of gas erupting into space much farther from the sun. The largest CMEs can contain billions of tons of solar material and are launched from the sun at up to 3,000 kilometers per second, according to the NOAA's Space Weather Prediction Center. This material contains an embedded magnetic field. It's this natural EMP field that causes the same kind of destruction that the E3 portion of a nuclear weapon-generated EMP would cause. But how dangerous are the EMPs generated by a coronal mass ejection? The most well-known CME is one that occurred over 2 days, September 1st and 2nd, 1859, and created the largest geomagnetic storm on record. We didn't have a sophisticated energy grid at the time, but the US did have a substantial telegraph system with wires strung from coast to coast. Since the third component of an EMP is made up of longer wavelengths, the lengthy telegraph wires were the perfect conductor for such energy. Reports of telegraph operators getting their hands burned were common, and some telegraph offices were set ablaze from the sparks emanating from their sets. The northern lights, also known as the aurora borealis, were witnessed as far south as Cuba and Honolulu, while the southern lights, the aurora australis, were seen as far north as Santiago, Chile, according to National Geographic. Telegraph operators discovered that the auroral current was strong enough that they could transmit messages without being connected to their batteries. And while most CMEs take up to 3 days to travel to Earth, the Carrington CME traveled over 150 million kilometers between the Sun and the Earth in less than 18 hours and unleashed its force across the entire planet. According to a NASA spaceflight, researchers from the British insurance company Lloyd's of London and Atmospheric and Environmental Research Agency in the US have estimated that if a Carrington-class event struck today's heavily electrified world, it would cause between $1 trillion and $2.6 trillion in damages just to the US alone. Multiply that number by 3 or 4 times if it lasted long enough to catch Europe, the Middle East, and China. There was a recent CME that happened on March 12, 2023, though on this occasion the Sun was facing away from the Earth, and the CME roared off harmlessly into space. If it had been heading our way, the Earth could have faced widespread blackouts, burned out satellites, and a complete failure of the internet for weeks or even months on end. As CMEs roar through space, they can create a shockwave that can accelerate solar particles along the CME's path to incredible speeds, similar to the way surfers ride along an incoming ocean wave. Known as solar energetic particles, or SEPs, these speedy particles can make the 93 million mile journey from the Sun to the Earth in around half an hour. Though SEPs are commonly detected following Earth-facing solar events, they are less common for eruptions on the far side of the Sun. Nevertheless, satellites orbiting Earth detected SEPs from this March 2023 eruption beginning early in the morning of March 12. meaning this CME was powerful enough to set off a massive cascade of solar particle collisions that reached the opposite side of the Sun where the Earth was. NASA's astronomers are still analyzing the data from this event to discover how such an impressive and far-reaching effect occurred, and whether we might see such effects in the next 2 years of increasing solar activity, leading up to the next solar maximum in 2025. We've had other near misses from CMEs through the years, as well as being affected by weaker CMEs. One weaker CME struck the area near Quebec, Canada on March 13, 1989, which erupted from the Sun 4 days earlier on March 9th. This CME caused widespread power outages as well as shortwave radio interference. There was another on July 23, 2012, a massive and potentially historically damaging solar superstorm, but this one luckily missed the Earth. Many astronomers believe the 2012 CME would have been a Carrington-class event if the Sun had been facing us at the time. Another massive CME erupted on October 14, 2014. It was strong enough to be detected on Mars on October 17, where it was observed by the Mars Express, MAVEN, Mars Odyssey, and Mars Science Laboratory missions. By October 22, at 3.1 astronomical units distance, it reached the Rosetta spacecraft that was approaching Comet 67P Churyumov-Gerasimenko, perfectly aligned with the Sun and Mars. And by November 12, it was observed by the Cassini spacecraft as it approached Saturn, a surprising 9.9 astronomical units away from the Sun. 3 months after its initial eruption, it even reached the New Horizons spacecraft, which was approaching Pluto at 31.6 astronomical units. CMEs become more frequent during the Sun's 11-year solar maximum. At solar minimum, the Sun might kick out about 1 CME a week. But as the Sun nears its solar maximum, there might be as many as 2 or 3 CMEs launched per day. The chances of the Earth eventually being in the crosshairs of a future globe-affecting CME is undeniably 100% certain. The one good thing about CMEs, if there is one, is the narrow window of predictability we have. Using our vast fleet of solar-observing satellites and Earth-based telescopes, astronomers can detect an incoming CME and warn various systems in its path. Electric companies can redirect power, airlines can reroute flights, and anyone using satellites for GPS location or communication can be prepared for any anticipated loss of contact. None of the countries of the West are truly prepared for any sort of EMP attack, whether launched by an adversary like Russia or China, or even a weaker coronal mass ejection from our Sun. To be fully prepared, each country would have to be willing to spend tens of billions of dollars to protect their electrical grid and to harden the vast number of electronic devices that its citizens depend on. From cell phones in cars to internet cables buried beside our roads and the GPS satellites overhead in our skies. As bad as a nuclear weapon-initiated EMP attack might be, a bullseye coronal mass ejection would be far worse, as its effects could extend across an entire hemisphere. And where a weapon-induced EMP attack can be an unlikely possibility, as we've only ever seen 2 nuclear weapons used in anger in the 78 years since the first A-bomb was tested, we know for certain that a solar EMP attack through a massive coronal mass ejection is an inevitability. We've seen how powerful they can be, and we risk our very civilization's future by ignoring their damaging effects. Maybe instead of earthbound countries bullying each other for their own petty territorial gains, we might choose to work together to protect the planet as a whole. Unfortunately, that seems like a very unlikely scenario in our current world. Now check out how Putin actually thought the war in Ukraine would end, or watch World War III, most likely things that will cause it, for a look at some worst-case scenarios.